Now that you're more familiar with bonding in general, we can look at the physical properties. So, explain the melting boiling point, the conductivity of covalent metallic and ionic compound. So, let's look first of all at the type of structures, and then we can link it to the properties. And melting point, boiling point, and conductivity are normally the ones that we focus on. So, covalent, we saw two different type of structures. We saw simple molecules. An example was, for example, water, carbon dioxide, okay, and giant structures. So giant structures, remember that are those are like this substance that it's made of many types of atoms that are strongly bonded together through covalent metallic or ionic bond. Okay, so giant structure, carbon exists in these giant forms, and graphite, diamond, which is both forms of carbons, okay, as well as silicon dioxide, okay, which is like sand. So graphite, diamond, silicon dioxide are examples to know about giant structures. Let's look at ionic and metallic. So ionic only exists as a giant structure. Another word for structure is lattice. So you may hear ionic lattice. So lattice or giant structure, okay. And metallic also exists just as a giant structure or giant metallic lattice. Okay, same thing. So let's think about their properties now. Before we get into that, I want you to think about when something conducts electricity. So to conduct electricity, think it as a movement of electrons. Okay, so we need a movement. Electricity can be conducted only when there are delocalized electrons. So delocalized electrons mean that they're free to move through the whole structure, or free moving ions. Delocalized electrons or free moving ions. So it's important that you think about these structures and if they have either of these, delocalized electrons or free moving ions. So simple molecules, where are the electrons? Can you think about it for a moment? The electrons are shared between the bonds. So there are no delocalized electrons. Are there ions? No, because it's a covalent bond. We only have non-metals, so they're not charged in this case. So they're not conductive in any state. They don't conduct electricity because they don't have delocalized electrons, no free moving ions. Giant structures of covalent, you need to think again about where are the electrons. Diamond and silicon dioxide, they're also non-conductive because the electrons, they're all bonded, yeah, with the in between the atoms, not conductive. While graphite, the structure, it is a little bit different, and because each carbon is bonded to three other carbons in this type of structure, looks like many hexagons and many layers of these hexagons, okay. And in this layer, so because each carbon actually is bonded to three other carbons, there is one spare electron, and this spare electron is free to move across the structure. So it does conduct electricity, okay? Because the electrons are free to move, or delocalized electrons. Ionic, there are no delocalized electrons. The electrons, do you remember where they are? They have been transferred from metal to non-metal, okay? Which means that they are non-conductive, but only when solid. So in the solid state, the atoms are very close together. So think about state of matter. They're close together, so the ions can move. But when it's in the liquid or in aqueous state, the ions, they separate and they're free to move. So conduct electricity when it's in liquid and in aqueous solution. Okay, why? Because there are ions that are free to move. So always think about where are the electrons. Metallic, giant structure. Do you remember the structure of the metal? We actually mention even in the definition the delocalized electrons. That's why it always conduct electricity because the electrons are delocalized through the whole structure. We looked at conductivity. Now let's think about melting and boiling point. So simple molecules. I want you to think about something. Water is H2O in every physical state when it's solid, ice, when it's liquid, and when it's water vapor, a gas. It's always H2O. So whenever you're changing state, you're not breaking the covalent bond, but you're breaking something else, and those are called intermolecular forces. So in the simple molecules, um, you don't break the covalent bond, but these intermolecular forces, and those are quite weak. That's why simple molecules they generally have a low melting point and boiling point. Okay, because there are weaker, and remember, those are called intermolecular forces. Okay, because remember, H2O is always H2O in every physical state. So this is the example to keep in mind. Okay, it's different in giant structures because giant structure you actually have to break the bond itself. And these bonds, they are very strong, metallic, ionic, and covalent. They're strong bond, so they require a lot of energy to break them, which means that generally they have high melting point and boiling point. Why? Because a lot of energy is required to break the bond. This is what will give you many marks in the exams, okay? Energy required to break the bonds. Okay, the next step, after you know all of the properties and you can explain them, you need to identify the types of structures from their properties. So, is that a covalent bond? Is that a simple molecule, giant structure? And this is the type of exercise that I mean. Let's take substance Q. Look at the melting point and look at the melting point. The electrical conductivity doesn't conduct a solid, neither a liquid, and it's also insoluble. Which type of structure do you think is? Do you want to take a moment to try? It's a relatively low melting point. I mean, we can't really compare it, but not very high. Not conductive and insoluble. It must be a simple covalent. A simple covalent molecule. R. High conducts. Notice that it always conducts as a solid and as a liquid. What must be metallic? It's your turn to for S and T. Here it means insoluble. Oh, actually, this will be soluble. Little mistake here. S, very low melting point, not conductive, which means that it doesn't have delocalized electron nor free moving ion, must be a simple covalent. T does not conduct when solid, but does as liquid. There is only one type of substance that does that when it becomes liquid, the ions are free to move, and this is ionic. So it must be a giant ionic lattice. There you go. I hope that is clear. If you have any questions, let me know.